We're just doing the general rule for the definition. 7? Fine. Oh. 20? 20. It says find the lines that are tangent and normal to the curve y equals the square root of x at x equals 4. So this is exactly what we've been doing, right? I'm going to do the difference quotient. The limit is h goes. If you wanted to use the alternate formula, you could have used the alternate formula here. I'm not a fan. I tend to use the difference quotient. Do y'all have a preference? I'll use whichever one you want me to use. Don't do the new one you said? Or, okay. All right. Just make sure you can recognize it, though, right? On like a multiple choice test. Okay. F of x plus h minus f of x over h. This is going to be 4 because it tells me at 4, right? So, say right because I was right. Thank you. All right, so I got the square root of 4 plus h. Ooh, I see why y'all had trouble with this. Over h. So if you multiplied by the conjugate top and bottom here, it doesn't work. All right, that's 4 plus h. Writers than math. I'm going to continue here. H times square root of 4 plus h minus 2 or plus 2. Remember here about the conjugates, if you ever don't know what to do and there are radicals there, try the conjugate. Even if it's just in the top to try to get rid of some stuff, because in this case, let me make sure I pull my limit down with each one. The 4's cancel, and then also that h, since that's the only thing left, we cancel with that h in the bottom. So now I have the limit as h goes to 0 of 1 over square root of 4 plus h plus 2. Yeah. So now I can put the 0 in, right? So 1 over square root of 4 is 2 plus 2 is 4. So that is the slope of the tan line. When x equals, what was it, 4? No, you're not. No, you're not. Then, it's still not letting you see, Camden? Or is it, I just, okay. Let's see. We need a point, so y of 4 would be 2. So you got the point 4, 2. Slope of the normal line when x equals 4 would be what? Negative 4. So I got 1/4 and negative 4. Here's my point. So just two different lines here. The tan line would be y minus 2 equals 1/4 times x minus 4. Oops. I went back to that original equation, y equals the square root of x, and it told me x equals 4, so I plugged it in to find what y was there. Yeah. Yes. Yeah. Robert, great day. It is a great day. Great and dreary all day, all week.
I can't wait for this hurricane. I love hurricanes.
It's gonna be one. We're gonna have soup this week because it's gonna get cooler. It's gonna be in the 80s, and I'm so ready to. Madison is jumping way ahead here. Maybe not. No. Y'all don't have it Friday. Teachers will be here. All right, give me other questions about your homework. Number 5. Numero 5. Don't skip 5 since you did it in number 1 with the difference quotient. You don't have to do it both ways. There's like 2 of them. You don't have to do both ways. 5 and 6. Yeah, good, good.
We just do a lesson in like 10 minutes.
Shut up! That. Why are you asking me that?
Education is not the No, he fails. Albert Einstein.
Who?
Mom got a letter.
Are y'all talking about Socrates or Einstein? Yeah, they're talking about somebody else. All right. I feel like I say all the time how important this lesson is. But this comes up all the time. You will definitely, this will probably be an FRQ, not just a multiple choice. I don't know that I've seen a year where there was not a piece of this as an FRQ at some point. We will get to it, Robert, unfortunately. That's all the FRQs are. All right.
I would love to ask that question.
Well, this one, the whole like second half of the class will be that. All right, here we go. Graphs of the derivative. Here's what you're going to do. We're going to do it two ways. One, given a table, we're going to sketch a graph of what we think the derivative graph would look like. And then given a graph, we're going to sketch what we think the graph of the derivative would look like based on graphs. We're going to do it two ways. We'll start with the graphs. Are y'all ready? Huh? No, this is part 2 of 2-1 today. We did part 1 on Friday. All right, let me give you, and if I feel like y'all aren't quite understanding, Khan Academy does a really good job, and I've showed that video before in here, but if you don't, okay. Let me try to explain it first as best that I can. Let me start with a graph. Let's just start with a basic, and in fact, I'm not even going to put the y-axis. I'm just going to put the graph here. Let's start with a basic. I want to turn it upside down. Sorry. Here's my graph of f of x. Now, if I asked you, what do you think, based on this, what would the graph of the derivative of f look like? Okay, so let's think about this for just a minute. What does the derivative describe? What is the derivative? The slope of the tangent line, right? So I have to think about this for just a minute. If I come to this point right here, and what I'm going to do is I'm going to come below, I'll say this is going to be the graph of f prime of x right under it, okay? If this were the tan line right here, is that slope positive or negative? Positive, right? Compared to this slope of the tan line, which one is bigger? The bottom one. Bigger slope, steeper slope, right? Bigger number. Like this might, for instance, this might have a slope of 5, and if it did, this one might have a slope of 4. Because as we move more towards the vertex, what in fact is happening? Getting more horizontal, it's flattening out. That's exactly right. So maybe at this point I'm up here, but then as I move over, my slope is decreasing, and it's decreasing up until it gets to the point of the vertex. And at the vertex, what do you think that slope is? Close. 0, right? It's a completely flat slope. So that's where it's crossing over right here, like this. And then what's happening on the other side? Okay. It's reflective, it's a negative slope, but whatever this slope is going to be the negative of that. Do you agree? Because it's a symmetric, right? So whereas this point might be here, then over here, it's the negative of that. Does that make sense? If this is like the x-axis, I'm going positive, negative. So what do you think? Now I need it to be continuous because my first graph, if the graph of the function is continuous, its derivative is going to be continuous here. So what do you think this is going to end up looking like? A straight line. It's linear. You're exactly right. So if I connected them, this would be the graph of the derivative. Because right as this keeps going down, it's approaching more of a straight line. That the slope's just getting bigger and bigger, maybe ever so slightly, but it's still getting bigger and bigger. Does that make sense? So we're looking at the slope. Each one of these points is corresponding to like a slope on here, right? It's positive but smaller. It's positive but even smaller, and in fact they're getting smaller and approaching zero. So at the actual vertex, it's zero. The number, right, because isn't that what derivative means? Slope of the tan. So we're graphing the slopes of the tan line at various points. Shall we do another? Okay. Until you pick up on the pattern, and you'll start to see that certain graphs have certain patterns to them. Go ready to do another one? Why would it be Wednesday?
We'll be able to get here, but I won't be able to. I'll make sure you don't get Oh yeah, your car got like. Oh, that's so. What happened?
Time this is f of x, and I want you to construct what you think the derivative graph would look like. And I gave you some points here.
So derivative would just be fx.
Not always. We're doing some easy ones to start with. I told you this is hard to wrap your brain around, but once you get it, it makes sense. You have to remember what the derivative does.
What does it do?
The derivative is the slope of the tan line. Does that help you? Let's look at these pieces that make up this function altogether, because this is a very rigid function here, right? It's like a piecewise that's continuous.
How close the y value? Like if the slope, like where does it? If it's the slope of the line, slope would be one number, right?
Right.
So I determine the y value.
But it's happening. The x's are happening at the same place. The y value is giving you the slope.
I know.
So this is still going to happen at between -3 and -1. But where I go height-wise is going to be whatever the slope of the tan line is at each point. You see what I'm saying?
Yeah.
And then same thing between here and here, here and here, and here and.
That goes down. That goes up.
Okay, so that's what you're thinking about. We can be a little more precise with this one because I've been given points. So what do you notice? And we talked about this very, very briefly the other day. What do you notice about the slope here as compared to the slope here of the tan line? They're equal, right? They're the same. And in fact, no matter where I go on this little line segment, do you agree that the slope is the same? Positive or negative? Positive. Could you actually find that value for this if you really want to? How could I do that? What's the slope here? What'd you say? It's 1, right? Up 1 over 1, up 1 over 1. Or 1 minus -1 over -1 minus -3. Right? What? Oh my gosh. That thunder, when it rolled last night, I thought it was like another earthquake. I know, I was scared. I was a bit scared. So, so between -3 and 1, the slope is always 1. Do you agree? Or between -3 and -1. All right, well, where is 1? 1 happens right here, so this, it's just constant here. Does that make sense? I might should have started with this one and then moved to the other one. Sorry. All right, what about the next little piece? I misspoke too. Just because the function's continuous doesn't mean the derivative is continuous. Or there's something there, right? What's the slope of this little piece? 0. Do we agree? So between -1 and 0, my slope is 0. Kind of like a step function, yeah. Well, no, I'm not going to connect them. I'm not going to, because I want it to maintain its functionality. So there's no way to connect those two to make it. All right, how about, I should probably do this, right? Not necessarily, yeah. Make them open. Well, because I know that the left-hand derivative does not equal the right-hand derivative. Therefore, the derivative is not defined there, but y'all hadn't learned that yet. All right, how about the next little piece? It's what? 3, -3. So I'm going to go down to 1, 2. Okay, I apologize. Thank you. Just from here to here, yes? Next one. One half? I don't know, I didn't calculate it. Yeah. So 1/2 between 1 and 5. Just like the limits, the limit from the left has to equal the limit from the right in order for the limit to exist. The derivative from the left has to equal the derivative from the right in order for the derivative to exist at that point. So at this point, for that to exist, my derivatives from both sides would have to be the same, and they're not. Yeah, all of them. I would do all of them as, yeah. Now go back and look at that parabola and see if that makes a little more sense. Yeah. Let's do another one. Okay. We still have to do tables, remember? Robert, great day. It was good. How was yours? Graph the derivative. If that's f of x, take a minute on your paper and see if you can graph the derivative. Now this one's not going to be exact, right? Because I don't have exact points. Okay, so you're exactly right, and that's kind of what I'm going through in my brain too. All right, so let's look. The first thing I do is I look at places where the slope's going to be 0, right? Right, because anytime I have a max or min like that, my slope is 0. Agreed? So are you okay? So about right here, the slope is 0, right? Agree, disagree? All the way up this side, until I hit this point, my slope is positive. Do you agree? So then between here, it's negative, and then to the end, it's positive. Agree? Okay. You're actually really close. That's what Lainey said. Okay, so I'm not just, at this point, I'm not just, bam, switching from positive to negative, or from negative to positive. So it's a parabola. It's easing into it is what it's doing. See how I'm easing into that negative slope, and then I'm easing out of the positive slope, and then I'm easing into the negative slope. Right, yes. Where do you think my max or min on my parabola is happening? Where it starts, well, that would be here, which is this point. The vertex on my derivative graph, on my parabola. This one's kind of hard. We'll talk about this a lot, but do y'all remember learning about points of inflection? Where the concavity changes? Right now it's concave down, here it's concave up. Y'all don't remember doing that? So the point where it changes, that's going to be my max or min on my derivative graph. We'll talk about that in excess a little bit later on. But I'm okay right now with you just recognizing that this is the graph of a parabola. It does something like that. Okay, so I know that from between here and here, I'm going to be above the x-axis because it's positive, right? Why? It's hard to start getting into these for real. You just have to remember that I'm continually, so if I just absolutely had no idea where to start with this, I'd be like, okay, here's a slope. It's a pretty steep slope, right? That's approaching a straight line. So it's going to be kind of high up on my derivative graph. And as I move closer to this, where it crosses over, it's getting smaller, right? So as I come closer to that point, I'm getting closer and closer to it being 0. And I'm just kind of thinking in terms of the parabola like that, if that makes sense. Again, we are dabbling our toes in this. This is a huge, huge, huge topic that we will cover consistently all the time. So right now, just some basics. You'll have some basic graphs that you'll sketch the derivative of, and then some tables. So let's switch over to tables. Do y'all need a break in between, or you just want me to go for it? Okay. And then I'll stop and let you work. If you have a table, gosh, I don't want to copy this whole table. My dot cam is not working. If you have your book, it's on page 109, and I will just start with all right, so this is an easy concept. It's just tedious is all this is. I will probably only give you one of these on your homework. I'm looking at table 2.1. Are y'all with me?
Yeah.
I'm not going to give you all the applicable stuff, I'm sorry. That first one. So what this is people in a room, the probability that they have the same birthday, 30 people in a room, or whatever people, I don't know. Anyway, the probability that they have the same birthday, and this table goes on and on and on up to 70. Okay. Essentially, what we're going to do is graph the derivative of this function. This is a discrete function. What does discrete mean again? Everybody remembers discrete? Continuous versus discrete in algebra, in pre-cal. Discrete's not continuous, it's made up of points. Okay, so this is a discrete graph, and I'm going to graph the derivative here. So since I'm talking about derivative, I'm talking about slope of a tan line, right? Yeah. I don't know the tan line here, so all I'm going to do is I'm going to do AROC to estimate the derivative. And whenever I graph it, my x is going to be the midpoint between the 2 points I'm looking, and my y is going to be the slope between those 2 points. So what do I mean by that? I mean, if I take these 2 points first, midpoint between 0 and 5 would be what? 2.5. Then I'm going to do the slope, because I'm kind of trying to, this is a discrete graph, so I want to go in the middle of them, and then I'm going to find the slope between the two to estimate the derivative there. Okay, so here, if I do AROC between just these two, I'd have 0.027 over 5, which would be what? 0.0054. And for the next one, how do I get what? That's 0.027 divided by 5. 0 minus this over 0 minus. So this time's halfway between 5 and 10, which would be what? And now AROC between these 2 points. So it'd be 0.027 minus 0.117 over 10 minus 5, which is what? And so on and so forth. This is not hard, it's just tedious. For the whole table.
And then what do you, when you graph it?
You can graph it, you can put it on the calculator and let it graph, but these are all estimates of slopes. Oh, yeah, sorry. Do y'all need me to keep going with this one? Okay, okay. I mentioned briefly left-hand and right-hand derivative. I'm not going to, remember that's with piecewise. I'm not going to go into definitions or anything like that. Just understand if you have something like, I feel like this was on your homework this weekend too. If you have something like this, I can find the derivative from each side, the slope of the tan line approaching each. And so to do that, I'm just going to do the limit as h approaches 0 from the left of, and I'm going to do u absolutely, yep. This is left derivative. Right derivative would be approaching from the right. Again, I don't spend a long time on this in this unit right here at the beginning because we'll spend so much time on it later. But just to check, same thing you've been doing. You're moving along. The good stuff comes here. Shortcut. Yeah, that's whenever I really like calculus, once we get to that point. I'm just all right on it up till then. All right, let me give you homework, classwork homework. Whenever you want to do it. Oh, okay. I'll give you a second. What do y'all think about 2-1? That's a wrap up of 2-1. 2-1 in your book, which takes us through really 2-3 here. Your book's written crazy. Y'all still copying? Y'all be happy. Great day. It's so much better than 150 degrees of like molten lava. I know. All right, 13 through 16. Those are matching. They give you the graph of the derivative. You match it with the graph of the function or vice versa. Okay, so there's not a lot of work there. There's not a lot that you have. There's only a couple where you're actually going to actually find the no. 21's for Robert to apply what he knows. All right, 22 is one where you're actually going to graph it. 26 is just like the one we did in class together. One table. And then I got to get your multiple choice and all. There's still a couple more in here I really want y'all to do, but I don't want to overload you.
Yeah, we got a lot.
Those are multiple choice.
I know I'm on calculator. No, we have like